You probably shouldn't get stuck on the moon at night. Of course, getting stuck anywhere outside of Earth is definitely not a good idea, but a lunar night is a story in its own right. Firstly, currently, it is somewhat realistic to get to the moon. At least much more realistic than going to Mars. Right now, there are not only active discussions, but also concrete actions being taken to return humans to the moon. Furthermore, if you were to find yourself, say, detached from a space station in low Earth orbit, at least you most likely wouldn't freeze. Quite the opposite, in fact. But the cold darkness of the 14-day lunar night... It is weird that no one has made a movie about this, or maybe I'm missing something. Naturally, if a person were to stuck on the moon at night, far from the base, cold wouldn't be the only thing to worry about. But if we are not considering a hypothetical scenario and instead focusing on how equipment should operate, bases should function, and people should live during the long lunar night, it's a pressing issue that scientists and engineers are actively trying to solve. More precisely, it has already been addressed to a certain extent quite effectively. However, if we aim for long-term human presence on the moon, much more needs to be done. There are already many interesting ideas and technologies being developed for this purpose. What threats does the lunar night pose? How can machines and people survive it? How has this been done before, and what do scientists and engineers plan to do in the future? We'll discuss all that and more today.
My name is Andrei, and this is Cosmos Elementary.
We have been exploring the moon for several decades now. However, if we want to take the next step and establish a permanent human presence on the moon, we still need to solve a number of problems and develop new technologies and improve the existing ones. Many of these problems also concern robotic missions. Today I won't discuss all of the difficulties, but we'll focus specifically on the issue of the lunar night. The moon, like Earth, rotates on its axis, which creates a cycle of day and night. However, the moon rotates much more slowly. Some people even think that the moon does not rotate at all, because we cannot see this rotation from Earth. But of course, this is because of synchronous rotation. Just like many other moons and even exoplanets, the moon completes one rotation on its axis in the same amount of time it takes to orbit once around its primary, in this case, Earth. So both day and night on the moon last for about 14 Earth days. Any spacecraft or base that finds itself in the lunar night not only loses a critical source of energy for powering various systems for 2 weeks, but also loses a crucial source of heat. The temperature variations between lunar night and day are immense. On Earth, regions with drastic temperature variations are deserts. During the day, it can average around plus 38 degrees Celsius or about 100 degrees Fahrenheit, and at night it can drop to minus 4 Celsius or about 25 degrees Fahrenheit. This happens for two main reasons. If we consider a classic sand desert, as most people imagine it, the sand itself plays a significant role. Because of its thermodynamic properties, specifically its specific heat capacity, it requires much less energy to heat 1 kilogram of sand by 1 degree Celsius compared to, for example, heating 1 kilogram of water. Many of you have probably been burned by hot sand on the beach. Now imagine a desert where there is almost nothing but sand. Not only does the sun heat the air, the sand also radiates heat back. But while sand heats up quickly, it also cools down quickly. And when the sun sets, sand quickly releases heat back. So without the constant heating from the sun, the sand can no longer scorch as it does during the day. The second factor is how dry the air is there. Water can indeed retain heat much longer. Humid air takes longer to heat up, but also longer to cool down. But in deserts like Sahara or Atacama, there is practically no water in the air. But what are the temperature variations on the moon? If on Earth the temperature variations can reach 40 to 50 degrees Celsius in extreme cases, on the moon the difference can reach up to 250 degrees Celsius between day and night, sometimes even more. This is at the equator. During the day, temperatures rise to 120 degrees Celsius or 248 Fahrenheit, and at night they drop to minus 130 degrees Celsius or minus 202 Fahrenheit, or even lower, and on the moon it can be even colder. Near the north pole of the moon lies the crater Hermite. It has areas of perpetual shadow, meaning they are never illuminated by the sun. The LRO spacecraft measured temperatures of minus 248 degrees Celsius or minus 414 Fahrenheit there. This is even colder than on Pluto, which is much farther from the sun, making it the coldest known place in the solar system today. I think you can already guess why temperature variations are so significant on the moon. I mentioned deserts on Earth for a reason. The lunar regolith also rapidly releases heat through radiation. Furthermore, not only is there no water in the air to retain heat, but there's also no air at all. Well, there is some atmosphere on the moon, but it's very close to being almost a complete vacuum of open space. Plus, the lunar night lasts not just a few hours, but 2 weeks. During this time, temperatures go much lower. Although in reality, given the conditions there, it doesn't take much time at all. Even on the lunar day side, simply being in the shadow, like behind a rock, causes rapid cooling. At the Apollo 15 landing site, temperatures were recorded ranging from 100 degrees Celsius all the way down to minus 180 degrees Celsius. The almost complete absence of atmosphere on the moon allows for stronger heating. Our atmosphere blocks a significant portion of solar radiation, so not all of it reaches the surface. On the moon, it's the opposite. Nothing interferes with radiation. By the way, we should clarify what we mean by temperature here. When we talk about the temperature on Earth, we typically refer to air temperature. On the moon, there is no air, and up until now I have been referring to the temperature of the lunar surface. Some time ago I made a video where I talked about whether space is really cold. But if by space we mean the actual vacuum of space itself, then it has no temperature. Temperature is a property of matter. Therefore, when any area on the moon enters the shadow of night, the surface and everything on it start to cool down, whether it's a spacecraft, a base, or a person. Considering they are made of different materials, they will cool down at different rates. Equipment can cool down to a temperature where it ceases to function properly, and that's when problems can arise. But still, we somehow have working interplanetary spacecraft, and continuous human presence in space is already established on the ISS, and also on the Chinese space station. Various parts of the ISS also experience significant temperature variations which are comparable to those on the moon. But the big difference is that the ISS never remains in shadow for such a long time. The ISS completes an orbit around Earth in 90 minutes, circling the planet 16 times in 24 hours, allowing crew members on board to witness multiple sunrises and sunsets. So the ISS is not continuously illuminated by the sun, only experiencing something like daytime for about half of its 90-minute orbit. But the station employs a complex system of thermoregulation and insulation to ensure that neither the equipment nor the people inside are subjected to such temperature variations. And also the station does not lose the sun to generate electricity for that long. And even some interplanetary spacecraft that travel far from the sun, where its radiation is much weaker, can operate for a long time thanks to modern solar panels. A prime example is the Juno spacecraft studying Jupiter. But during the lunar night, solar radiation isn't just weaker, it essentially doesn't exist for a long period. The faint light reflected off the Earth doesn't count. So like spacecraft traveling even farther than Juno, those intending to endure the lunar night need something different.
Probably somebody is already typing in the comments about radioisotope generators, but they are not the only option.
The Apollo astronauts never had to deal with the lunar night. They all landed on the surface when it was illuminated by the sun, and they were there not long enough for the night to begin. The Apollo 11 astronauts, Neil Armstrong and Buzz Aldrin, spent less than a day on the lunar surface, 21 hours and 35 minutes. The Apollo 17 astronauts spent more than 3 Earth days on the lunar surface, 75 hours. However, no humans have experienced the lunar night directly, but robotic spacecraft have encountered it. As I mentioned before, the lunar night presents us with two main challenges: cold temperatures and lack of access to solar energy for generating electricity. The problem of temperature variations can be addressed passively through the use of reflectors, radiators, and insulation, like a reflector on the windshield, a thermos, or a cooler bag. But also actively, for example using heaters, but they require an energy source to operate. On February 3, 1966, the first spacecraft to successfully land on the surface of the moon was Soviet Luna 9. By the way, Luna 9 was also the first landing in history on another celestial body. Luna 9 also captured the first ever photograph from the surface of the moon. Here it is. How did it survive the lunar night? Well, it didn't. It simply wasn't designed to endure it. It operated on the lunar surface for 75 hours and transmitted panoramas of the moon. On June 2, 1966, the first American spacecraft, Surveyor 1, made a soft landing on the surface of the moon. The spacecraft was powered by solar panels, so it stopped operating as soon as the sun disappeared. However, it had two compartments with thermal insulation, where temperatures between -18 and +50 degrees Celsius or 0 and 122 Fahrenheit could be maintained. This one and subsequent Surveyor spacecraft could be reactivated after the end of the lunar night, although the equipment gradually degraded over time. Surveyor 1 survived the lunar night, and not just one. It operated and took pictures during lunar days for a duration of 7 Earth months. Actually, as early as 1962, NASA launched spacecraft to the moon under the Ranger program. The third, the fourth, and the fifth missions were equipped with seismometers and were intended to operate for 30 days, which meant they would inevitably encounter lunar nights. However, all three missions ended in failure. After the Surveyor program, it was just a matter of time until the first human landing on the moon happened. By the way, the astronauts of Apollo 12 found the Surveyor spacecraft. They landed within walking distance of Surveyor 3, reached it, and removed some parts to bring back to Earth. This image from LRO spacecraft shows the landing site with the Apollo 12 lunar module visible here and Surveyor 3 here. And here is a photo of Pete Conrad standing next to Surveyor 3 with the lunar module Intrepid visible in the background. I can't even imagine how amazing it must have been, not only being on the moon, but also finding a spacecraft previously left there. Imagine someday people will reach Mars and encounter the rovers Curiosity, Opportunity, and other spacecraft there. Although people didn't stay overnight, they did leave scientific instruments behind, which were supposed to operate much longer than Surveyors. It was the whole set of instruments. For Apollos 12 through 17, this set was called ALSIP, which stands for Apollo Lunar Surface Experiment Packages. And Apollo 11 had a simpler version. So those packages operated for several years. The one left by Apollo 14 ceased functioning in 1976, while the others were shut down in September 1977. How were they able to last so long? They used radioisotope thermoelectric generators or RTGs as their energy source, not solar power. Specifically, the model SNAP-27 operated using 3.8 kilograms of plutonium-238. Basically, it was a nuclear battery. Not like in Fallout though, where there were microfusion reactors. That we haven't figured out yet. The operation principle of RTGs differs from nuclear power plants. Power plants use energy released from splitting atoms into smaller parts through controlled chain reactions. This process releases a significant amount of energy. The heat generated in this process heats water, turning it into steam that spins turbines and generates electricity. However, this process is complex and replicating it on a small space instrument is challenging. In RTGs, radioactive decay is used instead. Let me remind you that chemical elements have different versions or isotopes. Isotopes of the same element have the same number of protons in the nucleus but differ in the number of neutrons. Some isotopes are stable while others are unstable or radioactive, meaning they decay over time, releasing energy in the process. This is a piece of radioactive plutonium-238 oxide. As it decays, it emits light and generates heat. Similar fuel pellets were used in generators on the Moon. How is this heat converted into electricity? Here, thermocouples are used. Unlike nuclear power plants, there is no water and spinning turbines to generate electricity. A thermocouple is a fairly simple device. Thermo refers to heat and couple means that it consists of two parts made from different electrically conductive metals or alloys. In a conducting metal, there are free electrons. When we heat this metal, we add energy and the electrons begin to move faster. And in a different alloy, there is a different number of free electrons. If you connect them and heat them, creating a temperature difference, an electrostatic potential appears in these conductors, resulting in an electric current. This is called the Seebeck effect. You can even test it yourself. Take two wires made of different suitable alloys, connect them at one end, attach a voltmeter to the other ends, and heat the connected end. I'll leave a link to a video where this is demonstrated well and explained in more detail. When we use radioactive materials for energy production, a large amount of energy is immediately produced during fission, and a lot of fuel is consumed. RTGs generate much less energy per unit of time compared to other sources, but they do so consistently and reliably over longer periods. The astronauts retrieved toolkits from two pallets, each capable of holding up to 5 instruments, transported them to required locations, placed instruments on the surface which were connected to a central module. The module collected, processed, and transmitted data back to Earth. And all of this was powered by a radioisotope generator. A plutonium fuel pellet was stored separately in a special casing on the module's hull. It had to be removed and inserted into the generator. Here's actually a photograph of Alan Bean removing the casing with the fuel pellet inside, and below is the generator itself. The tools were equipped with insulation. Also, by the way, the toolkits could vary slightly between different Apollo missions. The most temperature-sensitive instrument was the PSE, Passive Seismic Experiment, a passive seismometer designed to study seismic activity and the internal structure of the Moon. Firstly, the longer it operated and the more data it collected, the better. This implies that surviving the lunar night was essential, since a single lunar day wouldn't suffice. Additionally, to obtain satisfactory data, the temperature fluctuations at the instrument should not exceed ± 10 degrees Celsius from the average temperature of 52 degrees Celsius. Ideally, it shouldn't exceed ± 0.2 degrees Celsius. Here's what the instrument looked like. More precisely, what we see is not so much the instrument itself, but its thermal insulation cover. It also has a skirt that extends in all directions, covering part of the surface to further reduce temperature fluctuations. This blanket is a multi-layer thermal vacuum insulation, consisting of 20 layers in this case. You have likely seen similar materials many times on various spacecraft. Conspiracy theorists often complain that spacecraft look like they are made of cardboard, tape, and foil. But such thermal blankets are actively used in space because in the vacuum of space, the only method of heat transfer is radiation. Such insulation with multiple layers of reflective and insulating materials minimize heat loss through radiation. However, for a sensitive instrument like the PSE, this insulation alone wasn't enough to operate effectively at night. Therefore, active electric heaters were also used. The first successful long-term robotic spacecraft on the surface of the Moon and the first successful lunar rover was the Soviet Lunokhod 1, which means Moon Walker. It survived multiple lunar nights and operated on the Moon's surface for 11 months. It had a quite complex temperature regulation system. All of the rover's equipment was housed inside this container, which was sealed, pressurized, and equipped with a ventilation system. The top part of the container served as a radiator cooler, and on the open lid there were solar panels. At night, this lid was closed to reduce heat loss. Additionally, the lunar rover was heated by radioactive heating elements using polonium-210. These elements were made specifically for heating purposes and not for generating electricity. So the lunar rover would simply rest at night and when day came, it would resume its work. China employed a similar approach and continues to do so. In 2019, for the first time in history, a spacecraft successfully made a soft landing on the far side of the moon. The Chang'e 4 mission comprises a stationary lander and the U-22 rover. Similar to the Soviet lunar rover, they shut down and were heated by radioisotope heaters at night, while electricity was generated using solar panels. It was planned that the stationary lander would operate for 12 months and the rover for 3 months. However, both of them actually remained operational for years. So in principle, we already have a number of examples of how spacecraft have survived lunar nights. So we have some working methods, and it seems that we just need to continue applying them further. However, it's not all that simple.
So we've established that one of the solutions is radioisotope generators. Moreover, there is considerable experience in using them. However, as I've said, this is not the only option.
As historical examples have shown, it is possible to rely solely on radioisotope heaters while powering systems with solar energy. The advantage is that this simplifies the system. However, this approach also requires shutting down a spacecraft during the night, which is acceptable in some cases but not suitable for certain instruments that need to perform continuous measurements, and for transport and human habitats, living life support systems without power for 2 weeks isn't really an option either. There is a slightly different approach, using batteries. During the day, we power devices with solar energy and charge the batteries. And at night, we use nuclear heaters for warmth and draw power from the batteries. Is it an option? Yes. However, here is the catch. Batteries weigh a lot. So, this design significantly increases the spacecraft mass and makes the mission much more expensive. And for the whole lunar base, it's even worse. Well, then you can fully rely on the RTGs. Use them for heating and generating electricity, especially since they have been used multiple times in space. Missions exploring deep space, Pioneers, Voyagers, Galileo, Cassini, New Horizons are old spacecraft that have operated and are operating for many years and even decades far from the Sun, which is possible thanks to RTGs. The modern version, MMRTG, is used on Mars rovers like Curiosity and Perseverance, allowing them to continue operating both day and night without concern that their solar panels will be covered in dust, which could prevent solar-powered based rovers from functioning. That's what happened with the Mars Opportunity rover and InSight spacecraft. Well, that's great, let's use RTGs and call it a day. But working with radioactive elements comes with a number of issues. The isotopes that have been used on the Moon, plutonium-238 and polonium-210, are highly toxic. This might not be as alarming for robotic missions, but could raise questions if used in the base with humans. The Apollo missions did carry plutonium, but it was encased in containers designed to withstand explosions during unsuccessful launches, landings, or atmospheric re-entries. When these elements were removed, astronauts didn't remain near them for long and returned to Earth shortly afterward. The plutonium fuel pellet from the unsuccessful Apollo 13 mission still rests on the bottom of the Pacific Ocean near the Tonga Trench. At least, there have been no reports of radiation spikes detected in that area. The additional problems with these materials are that they are not easy to obtain in large quantities, or rather just in any quantities. There are alternatives to plutonium and polonium, but some are less effective, while others require even more extensive protection. So RTGs, especially for a large base where people will live and a lot of energy is needed, are not the best solution. Moreover, they are expensive. Options without RTGs certainly complicate the design, but they are feasible. Surely someone has already thought of the option using solar power during the day and batteries at night. But here the problem is that we don't have active heating at night. In the best case scenario, there is thermal insulation. The example of Surveyor spacecraft showed that electronics can endure several lunar nights without heating, only relying on insulation. but batteries. If we're talking about commonly used lithium-ion batteries today, if you live in a region with cold winters, you might have experienced the fact that chemical batteries don't practically like cold temperatures below -20 degrees Celsius or -4 Fahrenheit. It is possible to both power and heat from batteries, but then the question arises, how many batteries are needed? This increases the mass and cost.
But there are also ideas to store heat in the materials that don't lose it as quickly.
So Regolith heats up to high temperatures during the day but also loses heat very quickly. Here, improvements can be made in both stages, heating more intensely and slowing down the rate at which it loses thermal energy. For example, we could make bricks out of Regolith.
Once, a long time ago, I camped out in a tent in spring when it was still cold. And to avoid freezing, I placed a brick that I heated by the fire into my tent. The tent was old and it was not made of synthetic materials but out of canvas, so it didn't melt. It actually did warm me up at the time, but of course now I realize how unsafe and stupid that was, so please don't do it.
Something similar has been proposed for the Moon, manufacturing bricks from Regolith on site, heating them during the day and using them to heat lunar habitats at night. We've already discussed thermocouples. They can be used without radioactive elements. Essentially, any heat source can be utilized for this purpose. It has been proposed to use multiple mirrors to concentrate sunlight into a single area, where temperatures would significantly exceed those achieved by regular heating of Regolith. Two elements with temperature differences can also store heat for some time and generate electricity. In addition to a thermocouple, a Stirling engine could also be used, which can generate electricity by utilizing heat and cooling cycles. Also, there was an idea to send energy to the dark side of the Moon from space. An orbital station would receive energy from the Sun and transmit it as a focused laser or microwave beam to a station on the dark side during the night. In principle, that could be done. Such a concept has also been discussed for Earth. There even was the British government project to build such a space-based power station. Here's another good idea. Yes, there are huge temperature variations on the surface, but do you know where they are not as extreme? Under the surface. The Apollo 15 and 17 experiments showed that at a depth of just 1 meter below the surface, the temperature is nearly constant. So we could bury parts or entire buildings or spacecraft underground. Some spacecraft could bury themselves during landing, though here we have to think about the power source. They could operate on batteries for a while. Alternatively, the spacecraft or an instrument could bury itself automatically after a soft landing. However, their functionality might be limited in such a buried state. Human habitats can also be covered with a layer of regolith on top, as shown here, or they can be built underground altogether. There's a similar idea to build Mars habitats in lava tubes. Underground caves formed by lava flows. They exist on Earth, Mars, and the Moon. They can be accessed through such openings, and these caves could serve as a protection from radiation, and temperature there could be more stable as well. There was a study that found a place on the Moon in such a lunar pit with a constant surface temperature. It is about 290 Kelvin or nearly 17 degrees Celsius or about 62 Fahrenheit. So building a base in such a location theoretically eliminates the issues of overheating and freezing. There's still a problem of energy, but at such temperatures batteries can be effectively utilized for nighttime power supply.
And I haven't mentioned the elephant in the room yet. I'm talking about the night. Not every region on the Moon has night.
There are shadowed regions of eternal darkness within craters and the polar regions. But also, there are areas that receive almost constant sunlight. This means that there is much longer access to solar energy. Additionally, those regions of permanent darkness seem to have deposits of water ice, and water ice is crucial for various purposes, including life support and fuel production. In general, another solution is choosing the right location. However, it is not solely limited to the poles, as there are other areas on the Moon where it may be necessary to place a spacecraft or even bases for specific tasks. So it's not just about nuclear and solar energy for heating and electricity on the moon. There are other methods available, and choosing the right location and placing equipment or bases underground can also mitigate the challenges of the lunar night. Some of the technologies I mentioned are already developed and in use, while others are still far from implementation. However, none of these ideas are impossible. When I made a video about colonizing Mars, there weren't many reasons for optimism, but here the situation seems to be a bit better. Lunar exploration is gaining momentum again, and we should see a human return to the moon quite soon. Who knows? We might even witness the first permanent human lunar base in our lifetimes.
Thanks for watching. Links to all of the sources are, as always, down below in the description, and if you enjoyed the video, leave a like, comment, subscribe for more videos in future, and feel free to share this video with your friends, family, and everybody else, so more people could see it. Thanks for watching, see you in the next video. Bye!